So this lab will cover diffusion and osmosis. In addition to this PowerPoint, you should have an understanding of what you saw in lab, both the demonstration up front with the potassium permanganate, as well as the dialysis bags that we had throughout the tables. So simple diffusion, again, is just movement of particles from a high concentration area to an area of low concentration. Simply put, if you put a drop of perfume in a corner, that perfume particles are highly concentrated in a corner, and they are not concentrated. The less concentrated, the farther you move out, and eventually those particles will spread just through random movement from where they initially were placed, area of high concentration, to everywhere throughout the room, area of low concentration. Another way of saying this is substances diffuse down a concentration gradient. If you drew a graph of this and had, high concentration versus low concentration, things will move from area of high to low. So they move down their concentration gradient. Naturally, it would take energy to move something against its concentration gradient, like when we see reverse osmosis. So the two factors from this page that you really want to know and understand are temperature and the steepness of the concentration gradient. The temperature was demonstrated with the potassium permanganate solution at the front of the class. You saw the purple spread much quicker in the warm water as opposed to the cold water. The steepness of the concentration gradient. Remember, each table had a different concentration gradient, and you saw the table with the 1.0 molar solution gained weight at a faster rate than the other dialysis bags. And of course, the dialysis bag with just plain water inside the 0.0 molar, that gained no weight at all. The 0.2 molar gained a little bit of weight, and with each measurement stage, each 10 minutes, there was more weight gained per in the bag with more solution. And again, the 1.0 molar solution gained more weight than the others. These other factors here are important in physiology, but the two that we looked at in class, again, were temperature and the steepness of the concentration gradient. It wouldn't hurt to understand the others. Membrane surface area, again, the greater the surface area, the greater the rate. And then my example for that was emphysema in class, where the alveoli in the lungs start to break down and you lose surface area. So then those people with emphysema, they have less diffusion of gases across that membrane because they've lost surface area. So that's why they have a harder time breathing. Osmosis is basically just diffusion of water, movement of water, but it has to be through a selectively permeable membrane. Usually water is the solvent that everything is dissolved in. We're talking about diffusion of a solute, but in this case we're talking about just diffusion of the solvent of water. So another way of thinking that water moves from where it is higher concentration to where it is lower concentration, water will move toward the side of that selectively permeable membrane with the more dissolved solids. So again, we'll demonstrate that in the next slide, but that's basically what we had with our dialysis bags. We had a dissolved solid, sugar, within the bag, and we had plain water, no dissolved solids, outside the bag. So what we saw water doing was moving into the dialysis bag. The way I always remember it is water wants to dissolve. So if there is a dissolved solid in something, water will move towards that dissolved solid. As I always tell my students in physiology, your body doesn't really move water. Your body moves salt, and then water follows. And again, this is critical for IV fluids. I might put a link on Canvas for the Emily Jerry story, and that would be a possible extra credit. If you could explain to me why that occurred. And again, the underlying this osmotic imbalance underlies a lot of diarrheal diseases throughout the world, and that is actually a fairly common cause of death in parts of the world is diarrhea. Basically, you get parasitic infections, and it eats at your large intestine. You cannot maintain your osmotic balance, and so you are just losing water faster than you can replenish it. And most water that's available in those areas is not fresh water. It's just more parasitic and infested water. So you end up basically dying of dehydration because you cannot replace the water that you lose fast enough. Okay, so side B in this diagram represents what is inside our dialysis bag. Again, we have solutes, different concentrations of solute, different amounts. So we saw different rates of weight gain in our dialysis bag. Again, the greater the amount of solute, the more rapidly osmosis will occur. So the dashed line that you see there between side A and side B is representing a selectively permeable membrane. So again, water moves down its concentration gradient. So in side A, water is at 100%. At side B, water is at something less than 100% because you also have the dissolved solids. So water will move from the side of pure water across that selectively permeable membrane to where there is dissolved solids. And the caveat has got to be the pores or the holes within that selectively permeable membrane are large enough to let water through, but not so large that they let the solute through. And most solutes that we're looking at are going to be larger particles than water. That's why we use sugar as a very large particle, and that does not pass through that selectively permeable membrane. Again, very important biologically. Basically, your body can regulate how much water passes through its cell membranes by installing little pores that, the more pores, the faster water will move. Osmotic pressure, again, is the kind of pressure generated by this osmosis. Just as you saw on the slide before, you can arrange it so that actually osmosis will draw water up a column against the force of gravity. That is referred to as osmotic pressure. Basically, the solution with the greater amount of dissolved solids will have a greater osmotic pressure. And you can reverse this by putting work into a system. If you have a piston and a semi-permeable membrane, you can put work into that and basically turn salt water into fresh water. Reverse osmosis filters are probably found on every sailboat that travels in the ocean, because if you're out and stranded, you cannot drink seawater. Seawater is 3.5% salt, and drinking that will dehydrate you and kill you. But if you had a reverse osmosis filter, you could put work into that and overcome the osmotic pressure and push salt water across this semi-permeable membrane. Again, salt being trapped on one side, water passing through the membrane, and turn salt water into fresh drinkable water. Because of the COVID and everything, we cut our classes short. I did not really go through this slide very much. This is more chemistry than you really need, but basically osmolarity is a measurement of the amount of dissolved solids within something. So our dialysis experiment, we had 1.0 molar solution. It was our strongest concentration, and 0.8 was less, 0.6 was less, and on and on. So it's just a measurement of how much dissolved solids is in a solution. That's really all you need to know about this slide, but don't fret too much on this. So tonicity is a concept that you need to know and understand. So these terms that we will look at, hypo, hyper, and isotonic, these are comparative terms. You notice this all says hypotonic or hypertonic solution. So this is comparing this is describing the solution that a cell or dialysis bag is in compared to the solution within the cell or the dialysis bag. So a hypotonic, the prefix hypo meaning below or low, a hypotonic solution has a lower concentration of dissolved solids than the cell or the dialysis bag that you're comparing it to. So basically, we had all of our dialysis bags in a hypotonic solution. We had some sort of dissolved solid within the bag, but outside the bag was just plain tap water. And again, the best example for us would be distilled water. Again, just pure water with no dissolved solids whatsoever. So you could either say the solution was hypotonic to the bag, or you could say the bag is hypertonic to the solution. Okay, just keep in mind those are descriptive terms. So, you've got to define what solution you're talking about. The solution, outside the dialysis bag, or the solution inside the dialysis bag. So again, a hypertonic solution, hyper, the prefix hyper means above or high. Just think of hyperactivity. A kid who has got a lot of activity is hyperactivity. He's hyperactive, not hypoactive. So a hypertonic solution has a higher concentration of dissolved solids than the dialysis bag or our typical cell. And again, this plays back to the Emily Jerry story. The solution that they put her cancer medication in, her chemotherapy drugs in, that was a hypertonic solution, or it was 23% hypertonic saline, as opposed to the 0.9% isotonic saline that the drug should have been in. That's what caused her death, was the drugs were in a hypertonic solution. So again, you need to know both what the solution, what the term describes as far as the amount of dissolved solids in a solution, and that should tell you where water is going to go. So as we saw on the page before, a hypotonic solution, water will rush into the cell and cause the cells to swell and eventually burst. A hypertonic solution draws water out of the cell and causes the cell to shrink and what we call crenate. An isotonic, prefix iso means the same, that is the same inside and out. So our only isotonic solution in our experiment was the one with 0.0 molar solution. It was tap water inside the bag and tap water outside of the bag. That was an isotonic solution. That's why that solution saw no change, no gain in weight. So our isotonic solution, as far as physiologically we're concerned, is 0.9 normal saline. That is what you should see everywhere in the hospital. Those bags are ubiquitous. That's what almost all drugs are put in, is 0.9 normal saline. That is our isotonic solution. So here's what happens to red blood cells exposed to different solutions. So the one in the middle is isotonic. That is a normal looking red blood cell, and the dark spot in the middle is a product of the fact that these cells are what they refer to as a biconcave disc. If you looked at them sideways, they would almost kind of look like a figure eight in the way. The middle kind of squeezes towards each other. It looks almost like a hemorrhoid donut, or one of those inflatable donut rings. The hypotonic, again, a cell placed in your hypotonic solution, water will rush into the cell because there's more dissolved solids in the cell. Water follows salt. And a hypotonic cell will swell and it could eventually burst as well. And again, that's distilled water is our good example of a hypotonic solution. On the right there, the hypertonic solution, the cell in the hypertonic solution, water will rush out of the cell into the solution because, again, water moves down its concentration gradient or follows a greater amount of salt. Water rushes out of the cell, and basically the reason the cell looks spiky is because those are remnants of the cell cytoskeleton. They are still, microtubule skeletons within the cell, and if that cell shrinks down, the skeleton's still in place. So you get this spiky appearance to red blood cells. Both being in a hypotonic and hypertonic solution are bad for your red blood cells and bad for your body. They can clot in certain areas and cause widespread stroke or heart attack if they clot in a capillary bed. So again, know what we did in class, understand what the experiments showed with regards to the dialysis bags and the potassium permanganate. And I recommend also looking at the video link that I'm going to place on Canvas for plasmolysis to understand what happens when you place a plant cell in a hypertonic and hypotonic solution, as well as any extra credit out of this would come from understanding the importance of this to Emily Jerry, and I'll put a link to that video as well.